Hello my dear students, let us start our today's class. Today first we will discuss conservation of momentum. Now according to the law of conservation of momentum, the total momentum of a system or an object remains constant if no net external unbalanced force acts on the system. That is, if external force F is equals to 0, momentum P will be constant. Now to understand the law of conservation of momentum, let us consider one example. Now consider a moving ball collides with another stationary ball lying on a ground. After collision, the moving ball will slow down and the stationary ball begins to move. The velocity and therefore the momentum of moving ball decreases after collision, and the velocity as well as momentum of the stationary ball increases. So when two balls collide with each other, then moving ball loses momentum and the stationary ball gains momentum. However, the total momentum of these colliding balls before and after the collision remains the same. This is the law of conservation of momentum. Next we will discuss how we can prove the law of conservation of momentum. For that, consider a system consisting of two bodies A and B of masses m1 and m2 respectively. And let these bodies are moving with velocities u1 and u2, where u1 is greater than u2. Now consider these bodies collide with each other after traveling a distance for a small interval of time dt. And during this time of collision, the body A will exert a force on body B, which is actional force, and which we can denote by FBA, means force exert on B by A. And simultaneously, body B will exert an equal and opposite force on body A, which is reactional force, which we can denote by FAB, means force exerts on A by B. And due to these forces, the momentum of the bodies changes. And let V1 and V2 be the velocities of body A and B respectively after collision, and where V1 is less than V2. So, initial momentum of body A is m1u1 and initial momentum of body B is m2u2. And final momentum of body A is m1v1 and final momentum of body B is m2v2. Therefore, total momentum of the system before collision is equals to m1u1 plus m2u2, and total momentum of the system after collision is equals to m1v1 plus m2v2. Now, according to Newton's second law of motion, force acting on body B by A, which is actional force, is equal to the rate of change of momentum of B. That is, FBA is equals to m2v2 minus m2u2 by dt. And similarly, FAB, that is force acting on body A by B, which is reactional force, is equal to the rate of change of momentum of body A. So, FAB is equals to m1v1 minus m1u1 by dt. Now, according to Newton's third law of motion, we can write FBA is equals to minus of AB, that is action is equals and opposite to the reaction. So, m2v2 minus m2u2 by dt is equals to m1v1 minus m1u1 by dt, or m2 v2 plus m1 v1 equals to m2 u2 plus m1 u1, or we can rearrange them and we can write m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. That is, total momentum before collision is equals to the total momentum after collision, and this is the law of conservation of linear momentum. Now, to understand the law of conservation of momentum, we will consider the example of recoil of a gun. Now, we have already learned the recoil of a gun, and which we have explained with the help of Newton's third law of motion. However, the recoil of a gun can also be explained with the help of the law of conservation of momentum. Now, the bullet inside the gun and the gun itself form a system. Thus, the system is gun plus bullet, and before firing, the gun and the bullet are at rest. Therefore, momentum of the system before firing is 0. And when the bullet is fired, it leaves the gun in the forward direction with certain momentum. Since no external force acts on the system, the momentum of the system, that is gun plus bullet, must be 0 after firing, from law of conservation of momentum. As initial momentum before firing was 0, therefore the final momentum after firing will also be 0. Now, this is possible only if gun moves backward with the momentum equal to the momentum of the bullet, and that is why the gun recoils or moves backward. So, what is the recoil velocity of gun? The velocity with which the gun moves backward after firing a bullet is known as recoil velocity. Next, we will discuss how we can calculate the recoil velocity of a gun. Now, consider mass of the bullet is equals to small m, and velocity of the bullet after firing is small v, and mass of the gun is capital M, and velocity of the gun after firing is capital V. Since the system is at rest before firing, therefore momentum of the system before firing is equals to 0, and total momentum of the system after firing is equals to momentum of the gun plus momentum of the bullet, that is capital M into capital B plus small m into small v. And according to the law of conservation of momentum, capital M into capital V plus small m into small v equals to 0, or we can write capital MV equals to minus small m small v. From this we can calculate the recoil velocity of the gun, that is capital V is equals to minus small m by capital M into small v. And here negative sign shows that the direction of the velocity of the gun after firing is opposite to the direction of the velocity of the bullet. And here see, recoil velocity of a gun is inversely proportional to its mass. Therefore, light guns recoil with large velocity and heavy guns recoil with small velocity. And finally, I have uploaded one video for you to make your concept more clear about the law of conservation of momentum. And this much is for today. Thank you.
After having studied the law of conservation of momentum, let's talk about its applications. When a gun is loaded with the bullet is fired, the bullet moves with a very high velocity. By Newton's third law, to every action there is equal and opposite reaction. Thus, gun recoils in the opposite direction. Since gun is much more massive than the bullet, it recoils back with very less velocity. Here, the mass of the gun is denoted by capital M, and mass of bullet is denoted by small m. As the gun is fired, the bullet moves forward with velocity of small v. As a result, the gun recoils back with velocity capital V. Now, according to the law of conservation of momentum, the total momentum before firing is equal to the total momentum after firing, that is, the initial momentum is equal to final momentum. Now, the initial momentum of the system is 0 because initially the gun and the bullet both were in a position of rest. Talking about the final momentum of the system after firing, so we can say it is equal to the momentum of bullet plus the momentum of the gun, that is small mv plus capital MV. Now if we rearrange the equation, we'll get the recoil velocity of the gun as minus mv upon capital M. Here the negative sign shows that the direction of recoil of gun is opposite to the direction of velocity of the bullet, so we can say the recoil velocity of bullet is opposite to the direction of motion of the bullet. The rocket works on the principle of law of conservation of momentum. The gases ejected from the nozzle gives a force upwards to the rocket. We can also apply law of conservation of momentum in case of rocket repulsion. If we ignore external forces, the momentum gained by the rocket in the forward direction is equal in magnitude the momentum of gases in the opposite direction. Thus the rocket and the exhaust gases push one another, and Newton's third law of motion is applicable in this case. Suppose the gases are ejected at a velocity of small v, and masses of fuel gases is denoted by small m. The mass of rocket is denoted by capital M, and it moves forward with the velocity of capital V. Now, according to the law of conservation of momentum, we know the initial momentum is equal to final momentum. Now initial momentum of rocket can be stated as mass into velocity. Initially the rocket was at rest, so its velocity was 0. So we can write the initial momentum of rocket is m into 0, that is 0. If we talk about the initial momentum of the fuel, initially the fuel was also at rest position. So we can say the mass into velocity of fuel, that is again 0, so initially momentum of fuel can be given as m into 0, that is again 0. If we talk about the initial momentum, that is total initial momentum, we can say it as sum of initial momentum of rocket plus initial momentum of fuel. The both are 0, so the total initial momentum is also 0. Now, final momentum of rocket when the velocity v is being acquired by the rocket. So we can say if we talk about the final momentum of rocket, we can say it as mass into final velocity of rocket, that is m into capital V. If we talk about final momentum of fuel, the mass of fuel is small m and velocity is small v. So final momentum of fuel can be given as mv. The total final momentum of the system, now it's given by sum of final momentum of rocket and final momentum of fuel, so we can say the total final momentum is equal to mv plus small mv, which gives us the total final momentum of the system. Now, if we equate, or if we substitute the values of total initial momentum and final momentum in this expression, we can say the initial momentum is equal to the total final momentum. If we rewrite the equation by more simplifying it, we can write the velocity of rocket that we denoted by capital V is equal to minus of small mv upon capital M. Here this negative sign denotes that the direction of velocity of rocket is opposite to the direction of motion of gas. So this is same the expression that we have already derived in case of motion of gun, or say required velocity of gun.